Thank you, Professor Tian, for the warm introduction. Hi, everyone. I'm Yi Xiao, and I'm from CHK Shenzhen. And it's a great honor to stand on the stage together with my collaborator, Yi Chiu from University of Hong Kong. This work was done when we were postdoc at University of Michigan and also UC Berkeley. Okay. So now let's talk about RDMA. I assume many of you have very well known about RDMA, which is remote direct memory access. It has many good features, for example, low latency, high bandwidth, and minimal overhead. So that is why it has been widely deployed in data centers in many workloads. To name a few, key value database, AI training, HPC, bulk data transfer, and so on. But, okay, sorry. Maybe I'll just take it. Okay, so, but these workloads, they have different service level objectives. For instance, for key value database, it is latency critical. For AI training, it cares more about throughput, whereas for bulk data transfer, it's usually considered as background traffic, so its SLO is best effort in many cases. Okay. But there's a trend that the workloads are collocating together, sharing the RDMA hardware resources. This is in a way to maximize the hardware utilization. So in the ideal world, we will hope that we could first provide strong SLO guarantees to all these workloads, and second, operate hardware at 100% utilization. But reality is harsh, because collocation often leads to noisy neighbor issues. For example, the workloads on the same RDMA-enabled end host, they will contend for the shared RNIC resources. Say they must compete for the port bandwidth, of course. They are also competing for RNIC caches and many other resources, which Yimin will talk about later. So the requirement here is that the workload should share resources in a context-aware and cooperative manner. But that is difficult. If we look at the existing RDMA framework, we find that they lack principal design to reason about the interaction between RDMA software and hardware layers. For instance, if we look from the application developer's view, the RNIC hardware is basically a black box, and we do know nothing about it. Instead, if we take a look from the RDMA hardware's view, the applications are also black box. It doesn't know any details of it, and it just considers various applications as competing entities that compete for the RDMA resources. So essentially, there's a big context gap between software requirements and RDMA hardware behavior. Right. So there definitely has been some efforts trying to solve this. For example, we can design our applications more carefully. Let's say we do not oversubscribe resources, and so we don't trigger any hardware issues. But that requires lots of efforts. Essentially, we need to modify every application. And each application, they are not aware of other collocated applications, so the performance will not be optimal. A second solution is, well, we can redesign the RDMA I/O. So RDMA I/O, they can coordinate between different applications, which is good, but it is not aware of application context, the internal details of these applications. It doesn't either know the hardware resources, so it cannot provide optimal coordination. A third solution is let's redesign the RNIC. We can redesign the RNIC driver, for instance, apply rate limit for isolation or other things, but this often requires a lot of changes to existing RDMA practice. For example, we need to modify their interfaces. So this brings up compatibility issues. Another solution is let's leverage the latest hardware programmability. For example, use the latest SmartNIC, FPGA, and so on. But a problem is that these program hardware are not always available, and they are not large deployed today. Okay, so overall, I have seen many point solutions for specific use cases, but they cannot generalize to more general cases. Or there are some general solutions, but they require extensive changes to the RDMA pipeline assumption. So is there a separate, a different solution? The answer is yes, and we present SwiftRDMA. So our insight is that RDMA resource sharing can be modeled as a scheduling problem. So the center of the SwiftRDMA is a scheduler. It takes inputs from various places and take actions. So first, it will take input from the operator with some policies. So these policies are basically the state machine that define when to perform what action. And then it will take signals from job workloads and also hardware signals. These define the current system status. So if the system status is not optimal, then it will follow the policies to perform actions to navigate away from this situation. And these actions include both data path action to RDMA IO runtime and also control path action to the RNIC resources. So then that is the overview of our system, and Yiming will tell more about it. Thank you.
Yeah, thank you for the introduction. So building SwiftRDMA comes with a set of domain-specific challenges. So first of all, we need to identify root causes of RNIC interferences. And that requires us to understand intrinsics of RNIC microarchitecture resource level details and to analyze different types of contentions or SL violations against these resources. And secondly, we need to find signals or actions as control knobs to actively mitigate these interferences. This is hard because we assume the usage of commodity RNICs, so there's no way for us to customize the signals or actions out of the box. And unlike CPU core scheduling, there's no way for us to directly control the RNIC resource units. So we have to resort for a set of indirect actions for precise control. And lastly, we need to enforce scheduling policies very efficiently, and that means we have to gather signals and take actions with very low overhead, and we have to scale well as the amount of workloads or connections grows. So now let me dive a little bit deep into the first challenge where we are trying to identify contention root causes. The RNIC comes with many different resource units. So to start with, we have NIC processing units or NIC PUs that drives the control, sending and receiving pipeline of the RNIC. We also have a set of NIC ports that directly connect and interact with the network fabric. The RNIC also comes with a cache that preserves frequently accessed metadata such as QP context and memory translation table. It also further comes with a user access region or UAR, which the CPU can use to ring the doorbell of the RNIC and initiate the sending pipeline. And our paper has proven that all of these different RNIC resource units can independently cause contentions or SL violations. But due to time limits, I will focus on the UAR contention. So to understand the root cause of UAR contention, let's first examine the workflow of a very simple RDMA send request. Suppose we have a send request for QP1 on RDMA IO thread. So what will happen is we will first try to ring the doorbell against the UAR page allocated for that QP. The NIC PU will then be notified and try to DMA payloads from the server. So far, so good. Now consider the fact that we have another concurrent send request for QP2 on a different RDMA thread, right? Then likewise, it's going to try to ring the doorbell on the UAR page. However, because the amount of UAR pages on the RNIC is very limited, it's very likely that these two different QPs are actually allocated to the same page. If that is the case, then one of the send requests have to wait for the other to finish because ringing the doorbell has to be an atomic operation. And in practice, this kind of UAR contention can lead to up to 57% of throughput degradation in our practice. And once we have found the root causes of different type of interferences, we can actively reset a set of signals and actions to mitigate them. Let's again take UAR contention as an example. So we have a set of trackable signals such as UAR congestion events and doorbell events. And we also have indirect signals such as a number of QPs per UAR page, which we can use to signify the amount of imbalance between different UAR pages. And once we have that, we can devise a set of controllable actions to actively load balance QPs across UAR pages and eventually to mitigate the contention. And similarly, we can instrument signals and actions for many other types of contentions and SL violations and eventually solve the problem. And in the paper, we also have an end-to-end scheduling pipeline where we use these signals and actions for actual mitigation. So please refer to the paper for more details. So in summary, our motivation is RDMA is essential for co-located data center workloads, but sharing of NIC resource could lead to severe contentions and isolation. So we are devising SwiftRDMA, which is trying to expose hardware resources for software-defined scheduling. And our key insight is to bridge the context gap between RDMA hardware resources and application-level requirements. And our near-term future goals will be to gather signals and take actions with very low overhead and enforce policies with high efficiency and accuracy. And with that, I'll conclude the talk. Thanks a lot for your attention, and we are open to all questions.
Okay, any questions? Do you have any questions? Okay, I have one question. What's the interface? I mean, can it be more simple? I mean, for example, when we exposing the network near contentions, we just give them very simple interface like the priorities, right? Priority 1, 2, 3, or you can give them this is absolute priority, right? Yeah. Or we can give them just another simple, just wait. 20%, 30%. What's the interface? I mean, it looks like you expose the NIC hardware very complex nature to the applications or users. Do you expose them or?
I see. The question is about the complexity of the interface for SL, right? So service level objectives. Is that so? Yeah. So I would say our interface is quite simple. Right now, it's just like a priority for different tasks. And apart from the priority, there's also this nature of different tasks where we can assign, whether this thing is latency sensitive or best effort. Right? That's the other signal. So it's a very simple interface overall.
Just very simple. Okay.
Yeah.
Okay. Okay. Thanks for the speaker.
Thank you.
Thank you. Maybe I will just sit here. Let me think. Control for RDMA. The presenter is a first-year PhD student in the Department of Computer Science and Engineering at the Hong Kong University of Science and Technology. He's from Kai Chen's group, and her research interests lie in data center networking with a particular focus on the host networking and smart NICs. Okay. We can stay here. First year students.
Yeah.
Okay, Qijing.
Hi everyone, I'm Li Qijing, and in this talk I will present to you our system named CARC, which is a catch-aware rate control for RDMA. This work is done in the IC lab of HKUST. RDMA has become a color store technology in modern data centers due to its high throughput and extremely low latency. However, recent work has revealed that the congestion arises in the last mile of the I/O path due to the inefficiency in the memory hierarchy. Before we dive into the I/O congestion, let us see a perfect scenario of a RDMA I/O path where no I/O congestion happens. In the receive side, NIC first receives packets in the receive buffers. Then the NIC fetches wookies in wookie cache or host memory to get the metadata like the destination memory address. And initiates DMA to the last level cache through DDIO acceleration, which enables DMA to bypass memory. After that, in step 4, application can access data in NIC directly and replenish wookie if needed after processing data. However, when I/O congestion happens, where ILC capacity is not enough, things are different. In the step 3, DMA operation will trigger DDL write allocate, which will allocate ILC space for new data and evac old data to DRAM. In the step 4, if needed data is evicted from ILC, application need to read from DRAM, which also bring eviction. As the receive ring space is used sequentially and repeatedly, there is a negative cycle. DDL cache eviction leads to net CPU cache misses. CPU cache misses bring new cache eviction and ILC occupies, which makes the DDL write allocate happen again. This process also makes the memory contention more severe, as there is memory bandwidth waste that evicted data will be used soon. All these things result in bad performance. Existing work like host CC introduce host congestion signal. The IO buffer occupies to traditional congestion control. Such solution is coarse-grained as it is not aware of the detailed cache occupies. It sends back a CMP once IO occupies exceed a threshold and lead to same rate reduction, which is 1/2 in DCQCN. In order to solve the IO congestion problem, we first modeling it. Here is a simplified case of cache replacement in network I/O, where the receiver uses 8 buffers for receive queue, and our cache policy is basically ILU. Assume our cache can accommodate 5 buffers. Among it, the DDL cache, which is marked as the dark, can accommodate 2 buffers, and non-DDL cache can accommodate 3 buffers. According to the DDL rules, when the DMA decimal address is not in cache, DDL will allocate space in DDL cache. Otherwise, DDL will put data directly to cache, no matter what the cache type is. Okay, now here is a receive side scenario. In step 1, in-cache memory are DMA'd to pre-post buffer. During this process, some data will be evicted from ILC, and in the end, the data 6 and data 7 will be in the ILC. And in the second step, application began to read the data 0 to 3 from the DRAM, which will also bring the eviction of unused data 6. In the step 3, ALIC DMA 4 new message to newly posted buffer 0 to 3. And there is no eviction happen because the buffer 0 to 3 already in ILC. And in step 4, application reads the last round message from DRAM, the message 4 to 7. As this pattern continues, the cache misses rate will keep at 100%. We model such IO congestion as a producer-consumer speed mismatch problem and represent the state transfer of cache system with the red figure. V1 here means the network ingress rates, and V2 here means the CPU processing rates. The states represent a different degree of unprocessed data volume, and the state transfer is decided by speed gap and time span. For instance, S1 means the unconsumed data size is less than DDL cache size, where no cache misses happen. S2 represents the unconsumed data size is larger than DDL size, but less than ILC size, in which case, those cache misses happen due to ALIC eviction in the beginning. After all buffers are read from ILC, cache misses stop. The last 2 states, S3 and S4, represent the unconsumed data size is larger than ILC size, but limited by receive queue size. This is the case of the example in last slides. In these 2 states, cache misses is 100%. Notice that in S4 state, network control mechanism like the DCQCN PFC will work to avoid leak queuing. And in this case, CPU has opportunities to consume massive message before new data arrive. So the S4 states can transfer to S1, S2, or S3 states. From this figure, we can note that the system will fluctuate among the 4 states. And more time spent in S3 and S4 means higher IO congestion. Narrow down the speed gap can slow down even avoid the state transfer. We choose two common scenarios of data center and increase the speed mismatch gap to validate our modeling. The scenario 1 is single flow with different application behavior. With tickets per packet increase, CPU processing rate decreases. And the scenario 2 is mixed flows with different network behavior. With number of long flows increases, network ingress rate increases. We deploy ERPC, a popular high-performance RPC framework, on 2 servers with 200 Gbps C++ NIC to conduct this experiment. From the figure below, we can see that with the processing rate decreasing or ingress rate increasing, the catch-misses line become higher and the end-to-end throughput performance degrades. Based on our modeling, we designed CAC, which is short for catch-aware rate control, to ensure speed match and avoid I/O congestion. The key idea is credit-based rate control. CAC maintains a credit pool for each RDMA connection, where each credit represents a catch line in receiver's LLC. When the sender sends an RDMA request, the CAC first checks the available credit and only posts the request to RDIC if the credits are enough. Otherwise, the request is blocked until credits are replenished. When the receiver finishes processing the data, it will trigger CAC to return the corresponding credit. By doing so, sending rates will match perfectly with receiver's rates, and our system will keep stay in the state 1 or state 2, where the catch-misses rate is low. Besides, in order to tolerate the coordination error due to RTT latency and I/O unrelated memory access, we introduce loosened credit to adjust the credit dynamically. For instance, to cover the RTT delay of credit return, loosened credit equals to RTT divided by request processing time, which with such subscription, we can eliminate the receiver idle time, as this figure shows. In our evaluation, we use same setting with previous validation experiments, and the results show that CAC can reduce tail latency by up to 1.4 times, and improve throughput by up to 1.35 times compared to host CC. Thanks for your listening. Any questions are welcome.
Okay. Any questions? Any questions? Okay. So let me see the title. It's the rate control for the I/O resource competition, or?
Yeah.
So what's the interaction between the rate control for networking contention and the NIC resource contention? What's the relationships between these two contentions? I mean, how do you solve them?
The network congestion control use the signal from the switches or the RTT delay, and my rate control is focused on the host cache resource. So we need to use the resources like the cache occupies. And the control.
So final results is the minimum of the two rate control. I mean, for each flow, the minimum of two, right? You have two rate control mechanism. One for the NIC resources, one from the congestion control. So needed to take the minimum, or?
Yeah, actually, my rate control congestion can work with any network congestion control mechanism, and the final result is take the minimum of them. The sending rate is limited by either by my rate control or either by the network congestion control, and the final result is the minimum of them.
Okay. KK, yeah.
EDIO trying to handle the cache. How important is this problem when you have larger scale? This seems like you're trying to deal with synchronous flows, when it's predominantly a small number of flows doing I/O, and you're trying to avoid the cache misses on the first and second level cache on.
Yes. This is a scalability problem, I guess. And in order to solve this problem, all mechanism do not use the basic credit that is limited by the IC size. We enable a Lucent credit, which enables the flows to have extra credit to DMA data, to send data. And this Lucent credit, I have a theoretical proof that to prove it, it will not overflow the IRC, because this is decided by the processing rate of a receiver, that if you have so many flows, but the processing rate is high, so you actually do not need many space to store your data. You can just use really small buffer size to acclimate your data, because receiver can process it very fast.
Okay. Okay. No more questions? Okay. Let's thank the presenter again. Thank you. 那个远程的接入了吗？不用。Okay. Our next paper is orderly management of packets in RDMA with Eunomia. The presenter is Sana Muhammad, a first-year PhD student at Johns Hopkins University. His research focuses on computer networks and in RDMA-enabled data center networks. And he is also broadly interested in building high performance and reliable data center systems. Due to emergent issues, he cannot come to here. So we will connect him through the Zoom. Okay.
To-enable data centers have become quite prevalent over the recent years. As of 2023, 70% of Microsoft Azure's traffic was over RockV2, and Meta has dedicated RockV to enable data centers for AI or LLM training, indicating that RockV2 has become an industry standard. However, despite its growing adoption and clear performance gains, scaling it in modern data centers isn't without a cost. And this is because RockV2 imposes strict in-order delivery constraint on the network. For example, if you have a flow and different packets of the same flow take different paths in the network and arrive out of order, like we see here, the out-of-order packets are not handled by the RockV2 and potentially dropped. As a result, data centers are restricted to use coarse-grained load balancing such as ECMP in the network, which delivers everything in order like we see here. This restriction has been highlighted in recent works. However, this constraint of in-order delivery has gained limited attention. For example, works like IRN, Convive, and Left all try to handle limited degrees of reordering in the network and solely focus on limited degree of enabling fine-grained load balancers. However, in this work, we argue that the limitations of this constraint go well beyond fine-grained load balancers and extend to many performance-enhancing techniques. Techniques such as irregular graph topologies like expander or jellyfish graphs that are known to improve the throughput of the network. We see a jellyfish graph here. These topologies contain paths of variable lengths. For example, we highlight the paths between switch 1 and switch 4 that are of different lengths. And these topologies then utilize fine-grained routing to leverage these paths better and inherently induce reordering in the network, something that RockV2 is not capable of handling. Another example of the performance-enhancing techniques include flow scheduling, such as pFabric or shortest remaining processing time, SRPT, flow scheduler that is used to prioritize latency-sensitive short flows. SRPT scheduler prioritizes the packets with least remaining bytes after them. So if a flow has multiple packets, its first packet will have the least priority or the lowest priority, while the last packet will have the highest priority. Now, in a network, if we have a switch with SRPT scheduler enabled and we have two different flows or different sizes, we see that the SRPT scheduler prioritizes the short flow over the larger one, but also creates reordering among the packets of the large flow. And as a result, something that packets will arrive out of order at the RockV2 NIC, and it will not be able to handle them. More examples of these techniques include packet deflection that is used to mitigate hotspots in the network, and failover techniques or failure recovery mechanisms. We invite the viewers to refer to our paper for further elaboration on these techniques, but we do argue that all of these techniques improve the performance of data center networks but induce varying degree of reordering, and as a result cannot be directly employed in a RockV2 network. We now zoom into one of these techniques to evaluate how an existing state of Rocky V2 performs, and we use fine-grained load balancing, for example, to be able to fairly compare against existing designs. So in NS3 simulations, we use a clause topology of 1:2 oversubscription and use a per packet spray in the network for load balancing. And at 80% network load, we show flow completion times on the y-axis and for two different flow sizes on the x-axis. We start with ECMP to provide a baseline that does not induce any reordering, and then we compare it against packet spray, which is used directly in a Rocky V2 network. And we see that it significantly increases the flow completion times because while packet spray is able to leverage the paths better, the reordering that it creates is not being handled by Rocky V2, and hence we see the performance degradation. Next, we equip Rocky V2 with an ideal ordering layer, which can handle any degree of reordering. Equipped with such an ordering layer, we see that Rocky V2 enables packet spray to significantly improve the performance of flows compared to ECMP. But as we mentioned earlier, existing designs do enable fine-grained load balancing in Rocky V2 networks. So let's see how these designs compare against an ideal case. Starting with IRN, which is a loss recovery mechanism for Rocky V2. We see that IRN is not able to provide the high performance gains like an ideal case because it is not equipped to handle high degrees of reordering. Next, ConV, which is a load balancer and also provides in-network ordering support to Rocky V2. While it improves performance compared to ECMP, it is far from delivering ideal performance. Similarly, RDMA, which is multipath transport for Rocky V2 networks, performs similar to ConV or worse, which is far from ideal. Lastly, LEFT, which is an on-chip ordering support for RDMA. When paired with packet spray, we do see that LEFT improves the performance compared to other ordering designs, but is still far from an ideal case. So we conclude that no existing design is able to achieve ideal performance. This motivates the need to create an efficient ordering layer for Rocky V2 networks. And with this, we present Eunomia, an efficient ordering layer for RDMA. Eunomia is made with few goals in mind. For example, it should have a low memory footprint, it should have little to no latency overhead, it should be able to handle high degrees of reordering, and it should be a non-interfering design, which does not interfere other protocols running on the stack. Eunomia sits on the RNIC underneath the transport and consists of a receiver-side agent and a sender-side agent. The receiver-side agent further contains a reordering manager, which intercepts all of the incoming data packets and places their packet data directly into the application memory and ensures we have a low latency overhead because everything is on the packet's path. Next, for all of the connections that do not face reordering, Eunomia does not process them and passes them directly to the transport. But the connections that do face reordering, the reordering manager passes them onto a hybrid dynamic or HD bitmap module, which is essentially a reordering buffer to track out-of-order packets. The HD bitmap module is able to handle high degrees of reordering while maintaining a low memory footprint. This module communicates with the memory controller to efficiently traverse, update, modify the underlying physical memory to track the reordered packets. Memory controller allows Eunomia to have a non-intrusive design. Once everything is processed by Eunomia, the packet is passed on to transport where it is processed, and then lastly, the reordering manager will generate a control packet, for example, an acknowledgement or a selective acknowledgement based on the packet's order. In the end, the sender-side agent intercepts all of the control packets and ensures that they do not trigger the loss recovery if it is for an out-of-order packet delivery. This also ensures Eunomia to have a non-intrusive design. The key to Eunomia's design is a hybrid dynamic bitmap or the HD bitmap module, which is essentially the reordering buffer to track out-of-order packets. But instead of holding complete packets, the HD bitmap module uses 1 bit per packet to track whether or not it has been received in a bit array that looks something like this. So if you receive packet 1, we turn the bit corresponding to packet 1 on. Similarly, for packet 6, we turn that bit on. Instead of this linear structure, Eunomia actually stores the bitmap in a circular array, like so, to be able to leverage the benefits that a circular array has to provide, which is the efficient use of memory. For example, when we receive packet 0, we mark it, we have in-order delivery of 2 packets, which do not need to be tracked in this bitmap anymore. The circular bitmap flushes this memory and reuses it to track more packets. Now, packet number 8 can also be tracked in the same bitmap. What happens if we receive a packet that cannot be tracked in the bitmap? In that case, we increase the size of the bitmap. This is what makes our design dynamic. And in order to increase the size, we simply append a linear bitmap at the end of the circular bitmap like this. This is what makes a design hybrid because it is a hybrid between a circular and a linear bit array. Once we have this hybrid bitmap, we can easily track packet number 11 and turn the respective bit on. Once we have received everything in the circular bitmap, we merge the linear and the circular bitmap to create one big circular bitmap to continue to reap the benefits of the circular bit array. This design of Eunomia, the hybrid dynamic bitmap, allows it to handle high degrees of reordering without leaving a high memory footprint. We invite the viewers to refer to our paper for further design details. For now, we move on to evaluating Eunomia in NS3 simulations to answer two main questions. How does Eunomia compare to existing techniques? And does Eunomia successfully enable performance-enhancing techniques in ROCK V2? We start with fine-grained load balancers to compare Eunomia against existing techniques and use a per-packet spray. We show average flow completion times on the y-axis and varying network load on the x-axis. And here is the performance of Eunomia, a ROCK V2 network enabled by Eunomia with packet spray in the network. Compared to ECMP, we see a consistent improvement in Eunomia, and we observe up to 82% lower flow completion times. Compared to CONV, we again see a consistent improvement across all loads because Eunomia enables packet spray to boost the performance by up to 50%. Lastly, compared to left, we see that Eunomia and left perform quite similar at lower loads, but as the load increases, so does the degree of reordering, and left fails to keep up with high reordering. And we see that Eunomia ends up achieving more performance gains. For example, at 50% load, Eunomia performs 10% better or 10% lower flow completion times, and at 80% load, Eunomia ends up having 30% lower flow completion times compared to left, showing that it does perform better than existing techniques and close to an ideal case. Next, we test whether Eunomia enable other performance-enhancing techniques in ROCK V2 networks, and we evaluate flow scheduling. We use shortest remaining processing time, or SRPT flow scheduler that we presented earlier, and compare it against FIFO, first in, first out flow scheduling, which does not induce any reordering. At 80% network load, we show the average flow completion time on the y-axis for different flow sizes on the x-axis. So compared to FIFO, shortest remaining processing time actually performs worse without any ordering support. This is because it induces a high degree of reordering, which ROCK V2 is not equipped to handle. When we equip ROCK V2 with Eunomia, we see that it allows SRPT to provide the promised performance gains, which is lower flow completion times for latency-sensitive short flows, up to 86% lower flow completion times. And for the large flows, we see the performance remains the same, indicating that Eunomia is able to handle the high degree of reordering that has been induced for them. So we conclude that Eunomia successfully enables ROCK V2 data centers to leverage flow scheduling. In the end, we showed that ROCK V2 is rigid. Eunomia breaks this barrier by providing an efficient ordering support and enables many applications like load balancing, failovers, and flow scheduling in ROCK V2 networks. With this, we finish our presentation and open the floor for questions. Thank you very much.
Okay. We have one question.
Hello, I'm Xinle Du from Huawei. Great talk. I have a question about do you evaluate the hardware cost for the reordering?
Can you hear?
Yeah. So in terms of the hardware cost for the reordering manager, we do provide some statistics about this in this current work, where we evaluate how much memory we need for our bitmaps, and also to preserve the metadata for the bitmap. And we provide and we have tested it in FPGA simulations and evaluate for X number of concurrent connections in the network, how much hardware we will require. So while I cannot give you like the exact numbers for different connections right now, I can tell you that the way we calculate this is by for any active connection that faces reordering, we store metadata for that, which is around 20 some bytes, and then on top of that we have the reordering bitmap metadata. And for any concurrent number of connections, that can be calculated how much it takes.
Okay, thank you.
Okay, next question. Okay. Be close to the.
Yeah. Hello. So you mentioned ideal performance in the motivation scenario. So I'm wondering how, but you do not give the results in your evaluation to compare with your scheme with the ideal one. So I'm wondering how far are you from the ideal performance?
Yeah, that's a good question. So while I did not directly show a comparison with ideal case, we did compare the ideal case with the existing techniques, and then we can definitely create an indirect comparison between the two, because we see how far off or how worse or close an existing scheme gets to an ideal case, and then in our evaluation, we show that how worse or better, like for example, existing techniques are compared to Eunomia. So we can definitely generate this like indirect comparison that Eunomia does get very close to an ideal scenario. But yeah, there is no direct plots showing it. That's definitely something that we can add in a future work.
Thank you.
Let's thank the speaker again. Okay, thank you. Okay, now comes to our final talk. Final talk. 在哪儿跑了？看不。The final paper of this session is UCM, fast and maintainable user space RDMA connection setup. The presenter is Hui Jun Shen. She is a fourth-year PhD candidate at Hunan University. His advisor is Professor Guo Chen. Her research focuses on deployment and optimization of RDMA-based high-performance networking protocols and AI infrastructure architectures for next-generation systems. Okay. Let's start.
Okay, thanks, Professor Tian. Hello, everyone. I'm Shen Huijun from Hunan University. Today, I'm going to talk about UCM, fast and maintainable user space RDMA connection setup. And here is my co-authors from ByteDance and Hunan University. We all know that RDMA is the de facto standard for high-speed networks in modern data center. It is widely deployed in many productive apps like storage, recommendation, large language model in inference and training. For RDMA connection setup, there are two usual approaches. The first uses traditional socket APS, the same as regular TCP, while the second leverages RDMA CM APS for the libRDMA CM library. Just to add, the CM APS are based on sockets, but adapt for QPair-based semantics. Here's the key difference. The socket approach exchanges QPairs and other resources through a separate channel, completely different from the following data paths. Hence, we call it out-of-band connection. Well, the CM1 shares the same path with data transmission, and our analysis focuses on transmission efficiency, so we'll mainly talk about this in-band connection today. Let's see the whole process of RDMA transmission. The notable high performance of RDMA that we always talk about is referred to the right part of the picture with green lines. We call this RDMA fast path or data path. However, RDMA's control path at the left part of the picture is pretty low because it has to manage connections by kernel OS. When we focus on why RDMA control path costs so much, the most important part is the connection setup process. Because RDMA CM needs kernel driver to communicate with the RNICs for the packet processing. So during CM connection, there are a set of CM control options which are invoked through system calls to the kernel. However, these kernel calls are all long and difficult to observe. That makes RDMA connection setup process is inefficient and difficult to monitor. Specifically, we can see the inefficiency of RDMA connection management in these two metrics. First, for one single RDMA transmission, the latency of connection management is around 1 to 2 microseconds, which is much higher than real data trends we can see from the left picture. Then the high cost of RDMA CM will be worse with the increasing of connection number. As we talked earlier, the traditional RDMA depends on Linux kernel cores, which is complex and non-transparent. When we meet an RDMA connection setup warning or error from user, there's no ideas about which queue pair, which step, or which parameter. We have to take a lot of time reproducing, coding, and guessing. All of this lead to such a long resolution cycle, no matter bugs in lib or kernel. For most high-paid of productive apps with high latency requirements, that's intolerable. So our goal is to develop a new user space RDMA CM setup approach. Here is the original RDMA CM in Linux kernel. And we have two insights. One is to choose RDMA CM connection because as we talked before, it has unified APS and its in-band features which can help us to detect some potential path issues during the connection setup process before the real data transmission. The other is to leverage some recent user space technologies like DBTK or some libOS stack mode. That's our design, UCM, user space RDMA connection management. We can see in this picture, we want to make sure the whole CM process in user space only. Here's the UCM detail. UCM framework has two main models. One is work model and the other is monitor model. In work model, we set up and manage RDMA connections in user space. And in monitor model, we offer many methods to monitor and observe the UCM packets. Well, specifically in UCM work model, we met two challenges. The first one, how to implement the kernel bypass, and the second, how to support multi-thread for better performance. For the first question, we manage connections bypass kernel in our UCM library as a libOS library, which share the same address with user applications. And we leverage DBTK to handle packet processing, which means we can communicate to the NICs in user space without kernel. And for the multi-thread scenario, UCM leverages lock-free management. We use the flow steering features, which supported by most NICs. In this way, we can separate CM requests to different threads with QP number. We make sure that each connection's related information is accessed and management by only one thread. Well, in UCM's monitor model, we add some tracing cribs with USDT to get more information about connection status. And we also develop a capturing tool in UCM library for tracing UCM packets. Well, in our test bed like that, we evaluate UCM with these goals. First, we compare UCM's connection setup speed with the SOTA approaches, like the original RDMA kernel CM and the SE-CM. Well, second, we evaluate the impact of UCM's maintenance overheads on our productive applications. At last, I will showcase some successful maintenance experiences with UCM. Well, first, we deploy UCM in a large RPC framework in ByteDance. We can see in the picture that UCM performs many times better than the traditional kernel model. The extra overhead with enable our monitor platform is cost less than 7%. Well, now I will show some efforts from our monitor platform. With the UCM's monitor system, we can know the latency of every operation in online communication, in online connections, and we can see which one is the bottleneck in the UCM's process. Well, also we can, when we got some optimization and modify of one single option, we can also see the comparison of the bottlenecks operation. We can know whether the optimization works or not. At last, we can see we have two related works, KR Core and SECM. Our UCM need no special support from apps and NICs. There we can get a conclusion that UCM is the first pure user space RDMA connection management framework. We got dramatically accelerate RDMA CM setup efficiency, and we offer better maintenance for the RDMA production applications. At last, we hope that UCM will inspire more possibility for optimizing the RDMA stack at software or at user space. Thanks. Thanks for your listening.
Okay. Yeah, I have one question. Yeah.
I worry about security, isolation, and fairness when you do this.
Sorry?
So you're having user space set up the queue pair.
Yeah.
I don't know if this is a dumb question, but I worry about security where you have user applications setting up and you can starve out others, and how do you deal with fairness?
Okay, I got you. You are focused on the security when we put the queue pair management in user space, right? I think this question is related to our background. Our design now is only deployed in our own company, so I think the user we all already trusted. So we
So we offloaded this task onto a DPU and provided isolation. Might be helpful to think about that. Offline.
Okay. Maybe we can talk offline.
Okay.
Oh, one more question. Yeah.
Thank you for talking. I'm Wenxue from HK University. I have a question about what's the difference between your proposed design and the DPTK, and did you compare your design and DPTK, for example, bandwidth, latency, or I think the CPU saving is different?
You mean our design between DPTK?
Yeah.
I think our design is not some difference with DPTK. We just leverage DPTK to process our packets. We are not against DPTK. We have no performance compared with DPTK.
But I think the naive DPTK is that all control plane and the data plane are all in the user space, but your design, is that only control space in user space?
Yeah, yes.
Okay,
yes.
Okay, I see. Thank you.
Thanks.
Okay, that's all for this session. Let's thank the speaker again. Okay, so now I think we have a break till 11 o'clock, right? Mm-hmm. Yeah. 11 o'clock, we have a coffee break, and just take some fresh outside and be back in 11 o'clock. And for all the speakers of the next session, please come here, okay? Come here and just try your PowerPoint so we can save time. Yeah.
The entry information is constructed based on the mapping relationship. And finally, the new entry information is updated to the data plan. For example, when a server in the server cluster field, the latest mapping relationship is first collected, and then the latest entry is constructed based on the mapping relationship and updated to the data plan. This page shows that we use the traffic distributed by web search to conduct a load variance experiment between servers. It can be found that compared with other existing solutions, Meta have the maximum improvement of 60 to 70%. This page shows that the brain connection experiments. It can be found that when the threshold is 100,000, only X.54 kbytes of controllable fit memory overhead is needed to maintain PCC. This page shows that 5 FCT distribution is parameter in the Tofilo testbed. Meta have the maximum improvement of 6.25% in maximum FCT comparison to other solutions. In conclusion, we propose a lower layer followed balance strategy using hash selection and controllable filter to maintain collection consistency and the deliverability without scaling fine failures, providing multi-server for incoming collection with the help of hash selection and random selection. Experiment shows that the failures, PCC, and the deliverability of Meta. Thanks for listening. Any question?
Okay, questions? We have time for questions. So maybe I'll go first. So when you talk about fairness, maybe I missed it, but when you talk about fairness, can you clarify exactly what does it mean, fairness?
Fairness means that
Here, yeah.
If there are too many requirements sent to one server, where other servers are idle, the server with too many requests will be congested or overloaded, where other server may be idle, and it's a waste of resource, and will increase the waiting time of the other requests.
Okay. So in your evaluation, do you have like a metric to compare the fairness?
Yes.
Before and after?
Yes, we have 3 experiments of fairness, PCC, and deliverability. Meta increase max
I see.
60% of fairness.
Okay, any other questions? Okay, if not, let's thank our speaker again.
Thanks for listening.
Okay, so our second talk is about remote TCP connection offloading. Our speaker is Shuo Li. So Shuo is currently a PhD student from the University of Edinburgh. She is supervised by Michio Honda, and her research is mostly focused on networked systems.